Hi students. Here we'll continue from the discussion about resistors, series and parallel. You have learned about this in your IGCSE and SPM. So resistors, series and parallel. So we know that resistors are components which will against the charge flow in a circuit. So how this combination of resistors when connected in series and parallel will affect the total resistance in the circuit. So over here, we are looking at when the components are connected in series. So like for example, we have two light bulbs, two resistors connected in series to a battery. So this is a light bulb. So it's a source of resistor, okay, connected to a battery. And this is how the circuit for series. So now we are looking at the symbol we use for resistor. So symbol for resistor you can use as a wave ripple here, or you can use a square box. The circuit diagram for two resistors and battery. So this is a circuit diagram. This is the real diagram. Okay, so this is circuit diagram. Circuit diagram, we use the circuit symbols. So in this case, longer, positive, shorter, negative. So current flows in the circuit. Current will flow from positive terminal of the battery to the negative terminal of the battery. So you have a resistor R1, resistor R2. So you need to understand that we have discussed about the EMF and potential difference. So this is the EMF that is provided by the supply to drive the charges to flow in a complete circuit. So therefore, this EMF is provided for 1 coulomb of charge, for example, to flow around a complete circuit. So this is the energy given to the charge to flow. So when the charge flows, it's going to lose that energy, not all. So lose, because there's two resistors, it will lose the energy according to their resistance value and then return back to the cell. It's just like you are given a pocket money to go to school, and if you go to school, so you spend money at the food stall and to buy drink. So once you have spent all the money that is given, so you come back home. Next day you get the allowance again. It's like that. So it doesn't mean that it loses all the energy and it cannot return back. Okay, it loses the energy, so it will come back to get more energy and to complete the circuit. Therefore, I can say this potential difference, which is the EMF, is equivalent to the potential drop across the resistor R1 plus the potential drop across the resistor R2. So whatever the energy that is given will be equivalent to the energy that is lost. This is the EMF, and this is the potential difference. EMF is the energy given to move 1 coulomb of charge around a complete circuit. Potential difference is the electrical energy which is converted to other form of energy, example thermal energy, when 1 coulomb of charge flows around a complete circuit. So according to principle of conservation of an energy, whatever energy that is given to the 1 coulomb of charge to flow will be equivalent to the energy lost by these charges as they flow across the resistors or loads in the circuit. See, the next step, actually we can, because when they are connected in series, the total effective resistance of the circuit, it is the sum. So a circuit diagram of the equivalent resistance of two resistors in series, I can just combine them together, just add them straight. So if R1 is 10 ohm, R2 is 20 ohm, then the total effective resistance across will be 10 plus 20, you get 30. That is R1 plus R2. So this is the equation which we have actually related to how we can find the total effective resistance. See, over here we understood that whatever the EMF given will be equivalent to the potential drop across the components in the circuit. So you get an equation which is kind of based on principle of conservation of an energy. Energy given equals to energy loss. Then when you check the current that flows in the circuit, because this is only a single single loop, so current does not branch out anywhere. So current that flows through R1, R2, or any part of the circuit is the same. Okay, so it's the same. So therefore, if you were to use the Ohm's law, then if I take the current that flows through the battery, multiply by the total resistance in the circuit, effective resistance, it will be equivalent to current that flows through the R1. So that is I times R1 plus I times R2. That will be potential difference across your R2. Since the current are same, you can just cancel. That actually leads to the formula, my effective resistance equivalent to R1 plus R2. Okay, so the effective is equivalent to R1 plus R2. That's how we get to prove this equation. So, okay, so I suppose you have learned that. So this is based on principle of conservation of an energy. So for resistors in series, the concept that is used here is the principle of conservation of energy. Whatever energy given to charge to flow equals to the energy loss. But what is this? What is the electrical quantity which is the same, which is we are referring to the current. So that's why current will cancel off. Next, if you are looking at a parallel components in the circuit diagram, so represented by R1, R2 with a symbol and the power supply. So over here, you notice that when they are connected in parallel, current that comes through the battery, once it reaches to the junction, this junction here, it will split to R1 and R2. So it will split to I1 and I2. I1, okay, because it is flowing through R1. I2 because it is flowing through R2. So you just follow to make it easier. So in this case, I will have a formula. I, the current that flows out from the battery, is equivalent to the current that branches out at a junction here, plus I1 plus I2. Otherwise, I can also take this way. Here, this was going to be I1. This is your I2. They're going to meet at this junction and to give you the total I, which initially split at this junction. So at junction A, they will split. At a junction B, they will join. So whatever current that's flowing into a junction, equivalent to the current that's flowing out of the junction. And we understand current is actually the rate of flow of charge. Okay, so current is equivalent to rate of flow of charge. So whatever charge that flows out of the circuit will be equivalent to the charge that flows, means a charge which is splits at the junction and flows through the individual component. So in a way, for the resistors in parallel, we will use the idea of principle of conservation of charge, because whatever charge comes out is equal to the charge that returns. So the charge which splits at the junction. I can say the total current flowing into a junction equivalent to a total current flowing out of the junction. Okay. So then when you want to prove the equation for that, since I know the current is equivalent to is based on the principle of conservation of charge. But one thing you must understand, since they are connected in parallel, the potential difference across the resistors will be the same. So meaning delta V1 equals to delta V2 equals to the delta V, which is the EMF that is supplied. So therefore, I is equivalent to V over R. So this is the effective resistance equivalent to V1 over R1 plus V2 over R2. And we know that V1, V2, and V are the same. So I can cut off this. So when I cut, that comes to the equation here. So we have the effective resistance is equivalent to 1 over R1 plus 1 over R2, depending on number of resistors which is connected in series. Sorry, which is connected in parallel. Sorry, parallel. We're looking at parallel. So the current is a sum, but potential difference which is across each resistor is the same. That is the concept. So for the series, we are based on the principle of conservation of an energy. For parallel, it is based on principle of conservation of charge. Later, you will see how it is linked to the Kirchhoff law. So now come to the electric energy and power. So it's not new, something that you have learned. Electrical energy will be given by the power supply, which is related to the EMF. And power, we know it is the amount of energy per unit time. Okay, is the rate of work done or energy generated or energy loss. So this will be energy per unit time. Okay. So we know this is the energy. Which is EMF, and this will be the energy per unit time. So this is the formula you learned before. Power delivered by a source of EMF. So power is equivalent to, because from the definition of the equation, power can be, so we know that power is equivalent to electrical energy over the time. Okay, and then when we're referring to the electrical energy, okay, so potential difference is equivalent to work done per unit time. So the electrical or energy, so electrical work or energy is equivalent to the potential difference. Sorry. So mistake here. Clear that. So we know power is equivalent to electrical energy or work per unit time. And we know potential difference is defined as work done per unit charge. So electrical work, so it can be work or energy. So electrical work or energy is equivalent to the potential difference multiplied by the charge. So potential difference multiplied by a charge Q equals to IT. So that gives you the energy. So the power multiplied by the time gives you energy. So therefore, you know, energy is VIT divided by T. That's how you get to the equation. And since you're talking about the power delivered by the source gives you the EMF. So the current multiplied by the voltage is actually the EMF of the cell. So power dissipated by a resistor R with a current I and potential difference of delta R. Okay, so delta VR. This is the potential difference across the resistor. And this is the current that flowing through the resistor. Therefore, if I were to find the power dissipated through the resistor, it will be the current multiplied by the potential difference across the resistor, or the current multiplied by the resistance of the resistor. Otherwise, I will take the potential difference square divided by the resistance. I'm very sure you'll be able to know how to get these two equations. So because we know, okay, P equals to IV, that is proved, or VI, that is proved from this equation. And further, I can substitute your V from the formula V equals to IR. If I substitute in, I will get I squared R. And if I substitute your I with V over R, then I get V squared over R. All electrical appliances, you will notice there will be information given. For example, if you look at this, AC 100 to 240 volt and a frequency of 50 to 60 hertz and a power of 54 watt. So this specification must be given for the safety purpose. Okay, so also that we don't oversupply or too low power that is applied, which will not allow the system to operate at a normal, you can say, efficiency. Then, so here you can see then the range of the temperature it can operate, and all that information definitely need to be given. So over here, you probably have heard about the unit of kilowatt hour. This is the unit used to do calculations about the electrical energy supplied to our house. They will count as first 100 kilowatt hour. What is the rate? Okay, so maybe it is 2 cents. Then the next 100, it will be 25 cents. And then the subsequent, okay, will be 30 cents. So they have a rate. So, but then that is in the unit of kilowatt hour. Symbol K, small k, kilo, watt, an hour. So if I were to convert that to a standard unit of joule, so simple. Kilo, you take 10 power of 3. Watt, okay, so they already changed one. So you get a watt. So 1000 watt hour. Hour, okay, if you are going to give it to a standard joule, it has to be converted to seconds. So in 1 hour, you get 60 minutes multiplied by 60 seconds. So you have 3600. So when you multiply, that gives you a total of 3.6 times 10 power 6 joule of energy. So 1 kilowatt hour is equivalent to 3.6 times 10 power 6 joule of energy. Correct? So this is to conclude that if electrical energy, when you are looking at the power that is generated by the supply, which is the EMF, it definitely is going to be greater than the power lost from the resistor, because this is the source, the energy that is provided, and the amount of energy that is lost through the resistor will be actually lesser, because there will be some power lost through the other part of the components in the circuit. The wires overheat, and even the battery, when you talk about the supply, it may have an internal resistance. We already discussed in the earlier class. So due to the internal resistance, that will cause the power loss across the resistor to be lesser than the power generated by the source. Okay. So now we are coming into the Kirchhoff law. Okay, what is Kirchhoff law? Nothing new. I already taught you just now. Go back to the back slide. What is Kirchhoff first law? Kirchhoff first law is basically what you see here. Principle of conservation of energy. Kirchhoff first law is based on principle of conservation of energy. What I mentioned just now. I did mention the sum of EMF that is given is equivalent to the sum of potential drop across the resistors or loads in the circuit, closed circuit. So that's the definition for Kirchhoff law. Nothing new, as I mentioned. So Kirchhoff, you have, I will go to that first, the definition. Yeah. So Kirchhoff first law. So in an electric circuit, the total current entering a junction equivalent to the total current leaving the junction. See, this is the current that is entering, and this is the current that is leaving. So total current enters, which is I1 plus I2, is equivalent to the total current that is leaves. Okay, I2 plus I3. Okay, so in this case, when you refer to the Kirchhoff first law, Kirchhoff first law is based on principle of conservation of charge, because it is based on the current that is flowing in equivalent to the current that is flowing out. Okay, take note that. Sorry for the earlier phrase. Okay, so Kirchhoff first law is based on principle of conservation of charge. In an electrical circuit, the total current entering a junction is equivalent to the total current leaving the junction. Correct. Entering and leaving. Equation. Whatever current that enters, we take it as a positive sign, and whatever current that leaves, we take it as a negative sign. That's why if I further arrange this equation, I2 plus I1, if I bring this over, it becomes minus I2 minus I3, it will be equivalent to 0. Okay, so again, so I1 plus I4, so why in my pen, so I1 plus I4 minus I2 minus I3 equals to 0. Okay, so that is according to the Kirchhoff first law. The sum of current into a junction equal to the sum of current flowing out of the junction. Otherwise, I can also use this base, I can also define based on this formula. So I can say that the sum of current at a junction is equivalent to 0. Correct? 0. The sum of current at a junction is equivalent to 0, because whatever current that flowing in is taken as a positive, so current that flowing out is taken as a negative. So definitely they will contra each other. So cancel, then you get the net is equivalent to 0. Okay, so this is the systematically to show that. Then remember, current flowing in taken as a positive, current flowing out is negative. This is the other way you can actually see, okay, based on flowing in and flowing out. So whatever that is flowing in should be equivalent to flowing out. So as I mentioned earlier, current is the rate of flow of charge. So whatever the number of charge that flowing into a junction must be equivalent to the number of charge that flowing out of the junction. Okay. Then comes to Kirchhoff's second law. So for Kirchhoff's second law, I didn't mention. Okay, so it is based on principle of conservation of energy. So that was the first thing I mentioned when I was referring to the series resistors connected in series. So in a closed loop, the algebraic sum of the products of the current and resistance equals to the algebraic sum of the EMF in the loop. It's now, yeah. In this. So the algebraic sum of EMF is equivalent to the algebraic sum of the potential drop across each resistor or load in the circuit. So whatever energy given is equal to the energy loss. So that is based on principle of conservation of energy. Relates to the Kirchhoff second law. So if you look at this, okay, so let's go to the example part of discussion. So this is Kirchhoff laws, first law, second law. Nothing new. You have learned this before, you have used this before. Now you are just introduced with the name. Okay, so with that, so we will end the section here. Okay, thank you.